Good morning. This mini lecture is to go over a handful of items from exam one. And we're going to do some multiple choice items that were pretty important. And we're going to look at the final calculation on the exam, the very last question, the stopping acceleration for the nickel. All right, the multiple choice items that we're going to look at are the velocity graph problem that starts you study two objects in motion. And then we'll talk about Galileo versus Aristotle and the states of motion. That was another multiple choice question. And then a multiple choice kind of mental calculation problem. Four forces on a car in a parking lot, etc. And we'll go over that one. And then finally, number four, the y coordinate for free fall trajectory. We'll go over that one. And there were two questions like that. We'll just go over one of them. Okay, the first one. You study two objects in motion, object J and object S. Each object has its own velocity graph with the same time and velocity scales. The slope of each graph is positive, in other words, upward and to the right. But object J's tilt angle is only 10%, and object S's tilt angle is quite steep, 85%. Which statement below is unquestionably correct? Object S is moving at higher speed than object J. Option B, object J gains a smaller amount of speed per second than object S. Uh, Option C, object S is moving to the right. Option D, object J is moving to the left. All right, let's set up our velocity graphs, time axis and velocity axis. Yeah, so the velocity axis is the vertical axis. So above the time axis, that for us means it's moving to the right. Below the time axis, that means it's, velocity is negative. That means it's moving to the left. All right, so this is for object J. And we don't know exactly where the velocity graph is, but it'll be something like this, 10-degree tilt and somewhere. And I'm just parking one up there in the first quadrant where it's moving to the right. Now let's do the same thing for object S. And this one has another velocity graph. We don't know how long it endures or where it is on the graph, but we do know that it's 85 degrees. It's pretty steep. Now the correct answer for this one is option B. And 46% of the class answered that correctly. Another 44% answered object S moving at higher speed than object J. That is incorrect. The other two options, C and D, had 9% and 1%. Right now we're going to go over these and why they're true, why option B is true and why the other the other three are false. All right, so the key factor or the key words in option B are that it gains speed per second. All right, now in a velocity graph, that means the steepness, in other words, the acceleration. How many meters per second of speed do you gain for every second of acceleration? All right, now the other way to think about that, steepness, rise over run, on a velocity graph, that's delta V over delta T. And delta V over delta T, that's the acceleration definition. So if I say that object J is gaining a smaller amount of speed per second, that means it's not as steep. And that is definitely true. All right. Now, let's look at the other ones. The other ones are false. And the reason that they're false is the given information in this upper box, the preamble to the question, it doesn't give you enough information to decide A, C, or D. So I call it ambiguous information. Right? So this one here, object or option A, and then option C and options D are a little bit ambiguous. And here's why. I mean, you don't know if you have this for your velocity graph for S, or maybe this for your velocity graph for J. All right. So object S is moving to the right um, is true for only a few seconds if the velocity graph of S is way down here. All right, object J moving to the left, if we don't know if it's up here in the first quadrant or not. And if it is up here in the first quadrant, you can't say it's moving to the left because up there it's moving to the right. So those two are out. Object S moving at higher speed, you can't even say that. The higher, you know, the higher the graph is, um, the faster it is. So it might be S, it might be J, but we don't know vertically, where those graphs were. So you can't for sure see object A is correct as well. So your money is option B, and because there is enough information to determine something about the steepness or the slope of those two velocity graphs, or wherever they are. Next question, multiple choice, Galileo versus Aristotle. Galileo proposed a state of motion with constant velocity and no external forces acting. Aristotle viewed constant velocity as possible under what condition? Whenever gravity acts, but in no other situation, that's option A. During the first second of free fall, that's option B. Option C, and in fact, it's the only kind of motion, that's option C. And option D, uh, Aristotle viewed constant velocity as possible, but only if an external force makes the object move. That's the correct answer. Now these other two, the other three, there's a distribution, 11%, 10%, and 3% of students in choosing those options incorrectly. And so this one is another question like the previous one, where the students that got good grades on their exam did answered it correctly, and students that didn't get it a good grade on the exam also answered this one incorrectly. So option A, B, or C. And that's why we're going over these percentages. Now the reason that this is true is just read up chapter 2.3 and think. It's in there. It's when we're talking about Aristotle and Galileo and their contention about motion. All right, next question. This one's kind of a mental calculation problem. Here's a little diagram for it. Four forces act on a 1,000-kilogram car in a concrete parking lot on University. 9,800 newtons of weight force downward, 9,800 newtons of concrete's rigidity force upwards. Those are the two big green arrows in the vertical dimension. 100 newtons of U pushing the car north, that's to the right, the yellow arrow. And then 80 newtons of friction pushing south against you. Okay, that's the one on the yellow arrow to the left. The question, what is the net force on this car? Let's take a look at what we got here. We got 9,800 positive and 9,800 negative for the weight force, and the minus sign indicates downward in this dimension. Now those two balance, and that's normally what happens if you're in a parking lot. You're not sinking into the parking lot or floating up above, away from the parking lot. You're stable, you're at equilibrium, at rest. So those two forces cancel. Now the other two forces, all right, so option D and option B are out because those are both, that's like saying, well, I do have some net upward or some net downward force, but that's not the case because they balance. All right, let's look at the two horizontal forces. All right, now pushing south, that's to the left, and we're going to give that a minus 80 newtons. And the north push from U is 100 newtons, and that's going to be a positive 100 newtons. Now, to figure out the net force, you just add them up like this. Negative 80 newtons plus 100 newtons is equal to 20 newtons. That's your net force. So this one's out, 99.80, and this one is in. That's the correct answer. So 84% of the students got this one right, and 8% voted for option B, 4% for option C, and 3% for option D. Now that indicates that you missed the whole idea of net force, and we had homework problems and discussion in the textbook about that. And I'd just like to end with this comment. The reason that all this works out nicely is why we carefully apply the plus and minus signs according to the directions. If it's leftward, give it a negative sign. If it's rightward or north, give it a plus sign, etc. And we did the same thing with the vertical forces. If you do that carefully, you can figure out a net force. In this case, 20 newtons to the north. Next question, multiple choice. The y-coordinate equation for free fall trajectory, which is given there, exemplifies an essential part of what scientists want to do. And option A is control the discussion of ideas. We want the opposite. We want to always be talking about different ideas. And, sometimes getting into an argument. Galileo was famous for arguing, but, a lot of scientists, they get into debates and arguments about what's actually true. What's the proper equation? What's the proper interpretation? So forth. So A is definitely out. Predict the future state of the system. Yeah, that's it. That's the correct answer. That's what Galileo was always talking about. And that's what we're talking about in this whole class. Option C, construct a history of mathematical understanding. That's out. That's a history book. Okay, it's nice, but it's not what that equation is about, not what scientists do. And option D is kind of a goofy option. Galileo and other professors want to elect Galileo or other professor to an informal political office, king of all sciences. So that's definitely out. Here are the proportions. Option A got 1%. The other popular option was option C. Now, this is a problem. This is a question where if you didn't really study carefully, you'll be tempted by C. And option D only got 1% of the class as well. So, if you did a good amount of study and did some thinking, you could snag this question. And 74% of the class did that. Because predicting a future state, that whole idea, it's all over chapters 1, 2, and 3. So, all right, last one. Let's do the calculation of the stopping acceleration for a nickel. Here's the diagram from it. And this is the verbatim of the actual question. You observe a coin at position x1 with velocity v1 equals 1.9 meters per second away from you, moving toward point x2 on the x-axis as shown. So we're going to assume that it's moving to the right. Okay, now we don't have to worry about the directions on this one. We're just going to try to find an acceleration. So the acceleration is going to be the opposite direction of the velocity. I mean, if it's a frictional force. And that's what we've got here. The coin's mass is 0.005 kilograms, which is about right for a nickel. And then the friction force, 0.031 newtons that acts on the nickel. And that's going to be to the left in the diagram. Although I didn't put it into the diagram, you could mentally pencil it in if you want. A couple things about this before we get into the actual calculation. You may have had different values for the friction force and the velocity v1. So those were two variables in this problem. But anyways, let's work with these ones. And let's calculate the stopping distance, stopping acceleration on the coin. So this is a little bit easier than a stopping distance. And stopping distance was a brain burner on the homework, but I didn't put it in there on the exam, although it will be on exam too. Stopping distance, stopping time, definitely. Anyways, we want to go to the nearest 0.01 meters per second squared of acceleration. All right, now the key word here to interpret is this one, acceleration. So we're either going to use what we know to calculate one of two things, Newton's second law, or maybe the definition of acceleration. So let's take a look at it in detail. Okay, here's the definition of acceleration. Now, if you look at, so we want to be able to fill in the top, fill in the bottom, the denominator, if we can. Now, you look at the numerator, delta V, and we're good. We're good up there. We got V1. And then, of course, V2, where it stops, V2 is equal to 0. So, yeah, definitely you can calculate delta V, V2 minus V1. Yeah, we got that. But now down here, this is where we have a little bit of difficulty, delta T, because the way that I wrote this problem, I didn't give you any time information. There is a time interval, and you can calculate it, but you can't calculate it directly from the information given. It's a few more steps down the line. All right. Um, so definition of acceleration is out. We're going to put a big X through that. All right. But maybe Newton's second law. Now, Newton's second law, F equals ma, here's the other version of it, A equals F over m. That'll allow us to calculate an acceleration. Now, let's see if we got this one. All right, and I'm just going to modify this. So the numerator is a lowercase f, which is the customary symbol for friction. And we definitely know both top and bottom there. So we're golden on this one. We can definitely get this acceleration. And in the example, I didn't ask you to give me a direction because I didn't really set up an X and Y coordinate axis on this, although it's kind of implicit there. All I wanted you to do was to find the size of it, right? Now, in reality, it's going to be a leftward acceleration, so it would have a negative sign on it. But I told you directly in the problem, don't put the negative sign there. Just give me the size of it, and that's what we're going to do here. All right, so let's fill in the top and bottom here. All right, the numerator is 0.031 newtons from friction, and the denominator is 0.005 kilograms for the mass of the coin. Now, I want to point out something to you. The numerator has kilogram meter per second squared right here in the red oval. That's the same as a newton. But the reason I wrote it that way for you is if you write it in kilogram meter per second squared, you can then see clearly that you can cancel top and bottom. Kilograms cancels from the top and bottom. But now the top, you still have meters per second squared, but that's lovely because that's what you want for an acceleration. Acceleration is measured in meter per second squared. So this is all looking good. Right now, all I got to do is calculate 0.031 divided by 0.005. And that comes out to 6.2. So the answer is 6.2 meters per second squared for this instance of it. Now, you may have had the correct answer for a different velocity and force, but this is how everybody did it that did it correctly. All right, that's the end of this mini lecture. And I'll just remind you now, it's time to tackle Module 2. I'll see you on the internet.